now. Hang on a second.
Okay, so I disappeared.
Oh, wow. I mean,
And then because I need to pause the other one once it goes on. Now, hang on a second. Okay. Okay, now let's. And let me share my screen. You can see that, right?
mhm.
I'll wait a minute to start. Let's see how many show up today. It's kind of a slow day today. Maybe I think it's kind of Eastern. That's the problem. But anyway, is Martin? Don't know if Martin will be here. Rosa, did the people in the consortium get the fact that there was a talk or not? Probably not.
Some of them they do.
Okay.
And I think many people look in YouTube.
Okay, that's perfect. Yeah.
And I don't know whether you can see how many
No.
participants.
I can see how many people see it on YouTube.
So many people go directly to YouTube.
Okay. Anyway, no problem. So let me start. So welcome once again to everybody to come back to the online SPICE-SPIN+X seminar. As you know, this is organized by my center here that I lead together with Karen City, and the SPIN+X SFB Collaborative Research Center led by Martina Schliemann, Roger Hillebrands, and Matthias Chloe. Again, if you have any questions, please go ahead and write them in the Q&A or wait until the end and raise your hands, and I will give you the floor once the talk is finished by our speaker. It is my pleasure to introduce Igor Mazin. He's actually perhaps not so known in our community, but very well known in the community of magnetism, but also astronomical related materials and ab initio calculations and first principle calculations. He grew up and did his PhDs in Russia, but then moved to the US some time ago. I won't tell you how long ago because that will betray his age, although probably the PhD does as well. Just to say that he has already his vaccine, yeah. And then was an NRL for a while, and then now a professor at GMU. He has a person of many talents and has received many accolades. But one of the interesting things is that he's also very artistic. In one of these cases, he has now a new hobby of reenacting famous artwork in here, and you can see here him and his wife after he probably didn't do something very good and misbehaved or something. So, so that will give you an idea of how the talk is going to go. So with that, I'll stop sharing, and please go ahead, Igor, and share your talk, and begin your talk whenever you have a chance.
So
great.
You can see
everything,
and you can actually let me change my laser pointer. Yeah, all right. So perfect. Thank you, Jairo, for the introduction. Thanks to everybody for coming. I see many big names here, whether they will be satisfied with my talk or not, and also people coming from far away all the way to Japan and Georgia and whatnot. So I hope to make it worth your time, but you will see. This talk is partially theory, but also a lot of experimental work from my young colleague Nirmal Gemire from our university, and also many other people participated, and particularly Rebecca Daly, who was the time postdoc with Jeff Lynn at NIST, helped a lot with important neutron scattering experiments. So this is the structure of the talk. I'm as Jairo mentioned, I'm sort of newcomer in this field, so probably most of you know this stuff better than I do, but just to remind myself and everybody, I will talk a little bit about this. So why, always when you prepare a talk, you always find some typos which you didn't see when you try this talk several times. Of course, Scalar spin chirality. Why did it say quantum here? I have no idea. Sorry about that. And then this particular magnetic pattern, which turns out to be apparently very important. Then there will be the case where we'll discuss in details, and I will also give you some other example to illustrate that this mechanism is probably very universal. So there are usually in metals, in standard bulk metals, three types of Hall effects are discussed. One is ordinary Hall effect, which is due to Lorenz force acting upon conducting electrons, and that is proportional to applied magnetic field. There is also been known for many years anomalous Hall effect, which is combination of internal exchange field plus spin orbit coupling. Interestingly, the full quantitative theory of this effect related to Berry phases and stuff is relatively new, but the point is that this adds another component to ordinary Hall effect, which is proportional to magnetization, usually. As we now know, that's not always the case, that this anomalous Hall effect may appear in materials which have a zero net magnetization, but for standard ferromagnets, that's the case. Important thing to remember here is that both R naught and RS are function or depend on electronic structure. So in principle, as applied magnetic field change the underlying magnetic pattern, which it always does, the electronic structure also changes. And an assumption that is often made in the experiment that these two numbers are constant through the entire course of your experiment of your changing magnetic field is not a good approximation. We'll get back to that later. One of the relatively recent addition to this list is what people call topological Hall effect, and that arises from a characteristic of magnetic pattern, which is called scalar spin chirality. Most of you know about that. That arises if you have a closed contour, so that electrons can travel around this contour, and this contour is not coplanar. That means that the triple product of these three vectors is not zero. Basically the idea is that an electron that traveling around this contour if it has to adjust its spin according to the underlying magnetic pattern, then it accumulates this Berry phase and correspondingly the Hall effect. There are a couple of things that worth keeping in mind is that theorists often speak about double exchange as a mechanism of aligning itinerant spin with the underlying magnetic pattern. That's of course a mechanism, but it's worth remembering that in density functional theory, for instance, the quantum electrons always follow exactly local magnetization for the reason that in DFT, this local magnetization is basically formed by the same electrons. That's what George Savatsky used to call piling of itinerant magnetic moment to make a local magnetic moment. And that's a good way to look at things if you speak about itinerant magnet, where again, where the same electrons which are mobile also are responsible for a magnetic pattern. And another important thing is, of course, that it's not just coplanarity is not enough. The coplanarity must occur in a closed electron loop. Now, a useful mathematical representation of the same idea is continuous approximation, where you consider magnetization as a continuous function in space, and then the numerical analog of this quantity would be this triple product, and with Kronecker, with Levi-Civita symbol, it creates a vector which is sometimes called topological field, and it plays a role of effective magnetic field in the theory of Hall effect. So if this vector is non-zero, then you get this additional contribution to Hall effect. Now it's easy to see that if you have a single helical spiral, I mean it says DS here because they were trying to depict, or we were trying to depict, a distorted spiral in small magnetic field, but it's still it's like this distorted helix. So obviously it's coplanar, so it cannot have, so B is zero. you can have two helical spirals propagating in two different directions. In this very simple math, show that in this case, this vector is still 0. A very common model for this non-zero scalar chirality are three helical spirals propagating in three different directions. Again, it's easy to show that this vector is not 0 then, and in fact, if the pitches of these spirals are close, then you get an analog of standard harmonic beats, which are skyrmions in this case. So this is one of the simplest way, maybe the simplest way to generate skyrmionic structure. One pattern which was paid less attention, as far as I know, is a transverse conical spiral. That's something that happens if you, say, start with helical spiral and apply magnetic field in the direction perpendicular to the propagation vector. That at some point, at some critical field determined by magnetic anisotropy, this spiral will flop into cycloidal spiral, which at the same time will cant towards the magnetic field, and that's this yellow column, which is called transverse conical spiral. Now, that's more interesting. That's clearly non-coplanar. However, if you actually put this equation on this spiral into this formula, you find that it's still 0. So one single transverse conical spiral, despite being non-coplanar, is not enough. But what is interesting is that it's enough to have two spiral, not three, one of which would be transverse conical spiral, say propagating along Z, and another would be a single helical spiral propagating in the perpendicular direction, for instance, like this mu here. Then you can calculate this triple product, and you actually find easily that there is a field in the x direction, and the field is proportional to the square of this helical spiral. Now, this vector, as you can see, is actually changing direction depending on in which, because this MZ projection, MZ changes from one plane perpendicular to the main spiral to the other. And also, if this additional spiral is propagating in one direction or into the other, these things cancel out. But that's still useful in some regime, as we will see. So now let me now switch gear and go into the particular case of an interesting material has actually become very popular recently, for a variety of reasons, and also part of a bigger family, but doesn't matter for this particular talk. So this is a structure. There are individual manganese layers, it's purple balls here. They form Kagome spiral, which is very often mentioned in connection with this material, even though it's completely irrelevant because this magnetic interaction within this layer is strongly ferromagnetic. And then there is complicated interaction between these layers, in particular because there are two different bridging layers. One bridging layer is pure tin and it's strongly or seriously ferromagnetic, and the other is mixed yttrium and tin, and that is actually for yttrium it's anti-ferromagnetic. In principle, you can replace yttrium with other things and you can tune it all the way to being also ferromagnetic. Now, that is a good metal. It orders antiferromagnetically into this spiral phase at about 345 Kelvin, so above room temperature. The spiral phases, I will show later the different ways to look at that, but it's basically like this. So you start with a spin, then it shifts in one direction a little bit, and then a lot into the other. So this red spin is nearly perpendicular to this one, and then it does again the same thing. So it's sort of like goes left, right, a little bit left, a lot right, a little left, a lot right, and it's a good metal. Now that these two gentlemen from Russia introduced an effective model of three interlayer couplings, J1, J2, and J3. And in that case, J1 is ferromagnetic, J2 is antiferromagnetic, J3 is actually also antiferromagnetic. So that model can be solved analytically in the mean field approximation. That's what they did. You know, that was this famous adage in 1970s that what's the difference between Russian physicists and American physicists. The Russian physicists do what can be done as it should be done, and American physicists do what should be done as it could be done. So they introduced this model and then solved it completely. It was a very nice piece of work. Again, this shows how this thing go, and delta and phi in fact have opposite sign for the range of parameter space corresponding to this material. As I said, orders antiferromagnetically, it does this thing, and it forms ground state at T0. It forms incommensurate helical spiral, which is close to commensurate 0.25. So it's approximately 8 manganese layer. It's a little bit longer than a little bit shorter than 0.26. The Q vector is a bit larger. So sorry. That's another way to look at that from the top. So this is first layer, second layer, third layer, fourth layer. You see, so it moves to the right, then moves to the left. That's how it goes. Now, if you look at the magnetometry, these are data from my colleague Nirmal Gemiri, that you can see that if the field is perpendicular, is parallel to the c-axis, so perpendicular to the helical plane, it just continuously, nearly linearly changes towards saturation. It doesn't show here at about 15 Tesla, it actually saturates in 20 and closer to room temperature, it saturates a smaller field. But it also has two phase transition only if you have magnetic field perpendicular to C. So that's understandable, because if H is parallel to C, then what happens is that your spins gradually cant towards magnetic field, forming this sort of umbrella structure, or longitudinal conical spiral, while if it's perpendicular to AB, then at some point it makes it spin flip into this transverse conical spiral. And then there is a second enigmatic transition, which is visible in magnetometry and even better in some other experiments. And the first one is at least spin order. So it looks like maybe two different spin flows, but why two and not one? So if you look at the neutron scattering data from NIST, very accurate, very good scattering data, then you find several interesting features. If you actually go increase your field going from up, then you can see here, it may not be very well seen, but you can see that at some point your magnetic, it's about 0.27 in this at zero temperature. Then at the first spin flop field, it changes a little bit, just moving to moving very little, but just increasing Q a little bit. But the intensity, which is a bit harder to see, but you can trust me that because it's logarithmic scale, intensity changes by about factor of 2. It becomes about twice less intensive. And then at the second transition, something more dramatic happens. The main signal jumps discontinuously to a commensurate vector of 0.25. At the same time, a satellite peak at exactly twice this wave vector appears. So why does it happen? Another interesting thing, which I will not be touching upon, but just have to mention if I discuss this material, is that there is also interesting additional effect that with raising temperature, this spiral splits into two. Very close, so it looks a little bit like beads of two different spirals with normal and with also with very small wave, very long wave vector. And at some point, it one of them it actually goes to antiferromagnetic collinear phase. But let's go back to the main features, and that is another way to look at that. That's actually this diagram shows differential magnetic susceptibility, and it indicates very clearly several different phases. So phase A is appears in low field and then closes at the transition. Phase A prime here, it probably related with this physics of which we don't fully understand of the second spiral, and it's a very narrow region. Phase B appears after first flop, that's this phase, and in sufficiently low field there is another phase E here, and there are also two phases which I think that Rebecca and Jeff have somewhat better idea now what they are. They appear only very close to transition temperature, so they're probably related to fluctuations and maybe some sort of manifestation of Merman-Wagner physics, because this material is magnetically very strongly anisotropic. So we will concentrate here on the three main phases, A, B, and E. So let me now describe density functional calculations that we did. So I was calculating total energy for a variety of different planar stakings and trying to fit them to the following Hamiltonian. One term is in plane, nearest neighbors ferromagnetic coupling, strong, and it doesn't really matter for the physics we are describing whether it's really only nearest neighbor or there are also further neighbors. The net effect is ferromagnetic. Then we have so that was then we have interplanar exchange, where we include some number of neighbors to fit. I found that you need up to 6 neighbors to fit fully density functional energies. Then you have a standard single site anisotropy. Then it turns out that an important term is Ising type of exchange between nearest neighbor layers. And for them here, I was including only this part for the strongest exchange coupling, which is a ferromagnetic part. And then there is, of course, Zeeman term. Wrong button. So these were the all exchange coupling up to 6 nearest neighbor that had to be included to make this fit work, and then JZ was only included on this nearest neighbor part. And this JP, which is intraplane coupling, was included on the nearest neighbor level. Now I had all these dots here represent different calculations. This is for without Hubbard U, that's technicalities. This is for various Hubbard U's, and this is the quality of the fit. So the quality of the fit is very high. There were 11 collinear structures to fit six parameters. And then additionally, spin orbit coupling calculations were done to find single site anisotropy and JZ. So magnetic moment as a function of U minus J is shown here. So it's the ordered saturation magnetic moment is about here, and fluctuating moment is probably about here. First of all, the system is strongly fluctuating, and the mean field magnetic moment, which is DFT moment, is strongly suppressed even if you don't include any Hubbard repulsion. Second observation is if you do this fitting, then apart from natural expectations that the nearest neighbor is the largest and the nearest neighbor's interaction is ferromagnetic in the strongest, the next strongest interaction, surprisingly, is a 6 neighbors and so on. So that reflects its strongly metallic character. So basically, I wouldn't go as far as called RKQY, but basically these interactions are mediated by screening by thin-red electrons, and similarly to RKQY, it's a pretty long-range interaction. However, now I will play American physics and say, well, you know, I cannot really do much of analytical work with this model, so I will reduce it. And I also, and by the way, this plot is showing the calculated helical spiral these two angles that I was discussing as a function of u minus j that I used. And you can see that at about 0.4, 0.5 u minus j, you get things pretty close to the experiment. These arrows show the experimental numbers. So in principle, I was using these values. The paradox is that now we know that the band structure is actually closer to experimental if you don't use Hubbard U at all. But that's not an uncommon artifact in DFT. So now the full model is this. I'm saying I will reduce this model by neglecting J4, J5, and J6. So reducing that to analytically solvable model of Rosenfeld and the other guy, J1, J2, J3, changing the value to reproduce the same ground state as a full model. And then this reduced model, I keep the single site anisotropy, which is incidentally easy axis anisotropy, not easy plane, and JZ, which is easy plane. And the minimal model will combine these two guys into one effective anisotropy parameter, which is now easy plane as in the experiment, and that the units are millivolts, incidentally. Now, what are the ramifications? First of all, we can see that it is a strongly Merman-Wagner system because Néel temperature, which is determined by this roughly this ratio is about 30 millivolt in energy units, while the saturation field is much smaller. There's strong parametric frustration because it generates these spirals, and as a in some sense not unrelated with these previous two facts, that there are obviously strong fluctuations, especially when you approach the Néel temperature. So now this is my minimal model, and there is this analytical solution I was talking about, where these are these two angles, alpha and beta. So this is the representation of this phase diagram that comes out from the condition for this arc cosines to exist. And again, that wasn't that original paper. In fact, if I start introducing U and changing it, that goes, interestingly, goes all the way around, but a large part of this curve is inside the spiral phase. Now, in this minimal model, I obviously have a spin flip because I have an isotropy. So if I start with a helix, then I apply magnetic field. At small magnetic field, this helix distorts, but susceptibility is rather low. And when if I apply magnetic field along Z, so along the spiral propagation direction, it's just continuously canting. This pure cycloidal spiral does not exist if I have easy plane material, but it flops from helix directly to transverse conical, which is this, and that's roughly the energy scale of this transition, which is close to where we observe it. But if you look at this model closely, you find that this very model, this minimal model, actually has another unexpected spin flop transition. It has two different coplanar solutions. One is this flat spiral helix, which I already showed you. So this is the spin rotates right and left, right, left, and so on. And that is getting distorted by the field, and that's one solution. This is a second solution, which is people often called fan-like phase. And that has quite interesting structure. The two spins coupled ferromagnetically in this layer are actually parallel. Then I have two other spins coupled ferromagnetically, and they are canted with respect to each other and nearly perpendicular to the previous two. Then I repeat the same as here, but with the same canting, but with a different component perpendicular to the field, and then the same here. Now, the interesting thing is that this structure, as opposed to any spiral, has two different periodicities. One periodicity is for My, which is perpendicular to this dashed line, and that is 1 by 1 by 4 because it goes, it's large down, small up, small down, large up, and so on. But if you look at mx, which is projection of magnetic moment onto the field axis, it actually has a higher periodicity. It has periodicity of 2. So this is how it happens. So this is these are these two distorted two coplanar solution. One is distorted helix, another is a fan phase. So the fan phase is initially higher in energy than helix. If you only consider this coplanar solution at some critical field, it becomes lower in energy and then continues as this fan structure until full saturation. Now, if I add now a possibility of spin flip, then without magnetic anisotropy, the system momentarily will flip into cycloidal spiral, and that red curve is always below the coplanar structure, so it would never happen. However, if you do have anisotropy, then this red curve should be scaled up to account for this loss of anisotropic energy, so it becomes higher here and clearly crosses the helical spiral here, so it becomes it's a first spin flop. Most interestingly, if you go all the way up to high field, and then so this is a blow up of the low field part, this is the blow up of the high field part, then you can see that these blue dots, which is this fan-like structure, actually crosses again and becomes lower energy than transverse conical spiral. So that is my second spin flop. So first it flops from helical spiral into transverse conical spiral, and then from transverse conical spiral to the non-spiral periodic fan phase. Now you can, I will bring back the Ising parameter, and we'll solve this again. That can be solved perturbatively, and you can see that in that case, flipping the spiral from, in that calculation I neglect counting, flipping it from helical to cycloidal actually generates a small change in the pitch, about 1%. Now, remember that the on-site anisotropy does not affect the spiral pitch, but JZ does. So then if you make this really primitive model, then it gives you something like this, which is not quantitatively in agreement, but that's not surprising given that we know that real interactions are long range and more complicated, but it actually is qualitatively consistent and shows these two transitions, one strong and one weak. In that case, now we can go back to the neutron scattering part and reanalyze that. And we fully understand it now because it starts with the helical spiral at this field here. It's a first spin flop. So first of all, you remember that when they shine neutrons, send neutrons beam along Z, that can only see magnetic moments perpendicular to Z, which is, for case of helical spiral, these are all moments. For the case of cycloidal or transverse conical spiral, it's roughly speaking half of them. Because of that, you have this discontinuous drop in intensity by a factor of 2. Which is interesting, they didn't notice at first when they look at the data. But when I asked them to replot that in not in logarithmic, but in linear scale, they found that it's exactly factor of 2. And in fact, then later Rebecca did a more delicate analysis, including distortions, and found perfect agreement with the experiment. And at the same time, you know, this magnetic vector, sorry, these are not correct numbers. I forgot to check. It's actually flips. It's actually 26 and 27. That came from some organ. Doesn't matter where. Anyway, it flips from 0.27, shifts to 0.28 or 29, roughly by this 1%, and that's this this yellow dashed line. And then at the second spin flop transition, which was barely visible in magnetometry, but is very distinct in neutron scattering, what happens is that your periodicity now becomes commensurate, exactly commensurate. This continues at 0.20, flips to 0.25, and the second satellite appears. And why is the second satellite? You remember we were discussing that the periodicity of magnetic moment along Y is 4, but periodicity for magnetic moment along X is 2, and that's the satellite. So this is now they see two different periodicities depending on whether neutron scatters is in Y plane or X plane. So this is all very nice. And now let's go back to Hall effect, which is probably arguably the most interesting part of that. So these are data from another group, but Nirmal has essentially the same data, even more accurate. I just didn't have time to replot them, but that's fine enough. And that what they called AFM1 and AFM2, because I didn't know what they were, it's now we know that this is transverse conical spiral and fan phase. And these colorings here represent the topological Hall effect. Note that this is not logarithmic, that's linear. So this Hall effect grows quite gradually, but it grows with both magnetic field and temperature. Now, the way how people analyze that, and that's actually on the left is now Nirmal's data, they look first at the total Hall effect, which is here. And then they say, well, you know, in the saturation phase, we know that magnetic moment doesn't change anymore. And as I say, experimentalists usually assume that the coefficient is a constant. So why don't we fit this high field part with a linear function in field and call it ordinary Hall effect. And then we will subtract this linear function. Then they say, well, we also know that there is a there's a part which is proportional to magnetic moment, which is anomalous Hall effect. So why don't we plot this magnetic moment and adjust this coefficient to reproduce the low field part? That's what we do. Then we subtract that, and what is remains we will call topological Hall effect. Now, there are, of course, several caveats to this procedure. In fact, if I do that, and they did that, then you can clearly see that you get some sort of artifact definitely in the helical phase, and there's probably something wrong is going on here also, because we know that the magnetic field transition is actually occurring here. And the reason is obviously because in reality, the neither RS nor R naught are constant. They are also depending on, they continuously depend on electronic structure. So the better thing to do would be to just try to somehow continuously interpolate between the two between these two regimes, one of which would be above the second spin flop and the other below the first spin flop. If you do that, you will get something like this. I will later show that done in somewhat more systematic way. And that would be, so this cyan curve is roughly what you need to explain, because that's a better approximation to topological Hall effect. Now, so why is that? As you remember that this is, and we have very good confirmation from neutrons that this range of fields where this topological Hall effect obviously occurs is a single transverse conical spiral which does not have scalar spin chirality. So how can it be topologically non-trivial? And let me remind you of the physics of a completely different system, completely different phenomenon. It says nematic transition in iron-based superconductors. Basically, you can have in the non-magnetic phase, you have spin fluctuations. You can have spin fluctuations there at pi 0 vector, this is red, or at 0 pi vector. At some point, what happens is that one set of fluctuations becomes excited more easily than the other, which is shown schematically here. And that without having any long range order, magnetic order, it breaks rotational symmetry. Moreover, you can induce this state by applying external strain well above the nematic phase transition. It's just that this flux that it will it couples simply in first order by Ginzburg-Landau with these fluctuations. So one set of fluctuations becomes more easily excited than the other. Now, how does it help us? So you remember that it is about here, so at high temperature, where we saw topological Hall effect. And you also remember I was showing that this is that you can derive this expression where this topological field arises if you add an additional spin wave propagating along y, and it's embedded in this constant term. So now, suppose that, not suppose, I mean, we know that this topological field will couple with external magnetic field again. So you can write easily, I think I should have it, oh no, sorry. Yeah, I apologize. I meant to put in here, but just simple thing. You take this expression with the unknown parameter mu square, which is the amplitude of this spin wave, which we consider to be dynamically excited or thermally excited, and put it into partition function, just calculate the expectation value. It's a very similar procedure to what we do when we calculate Curie-Weiss susceptibility, for instance. So when we do that, then we end up with this expression. So again, that's a very primitive, very simple thing, assuming that you just have two magnets propagating one along y and the other along minus y. And we see what is the probability of exciting one at the expense of the other. And it turns out that one is more easily excitable. And because the planes are so weakly coupled, we can make this separately for each individual layer. So that means that depending on the sign of MZ in individual layer, you will be selectively exciting magnets which are propagating along y or along minus y. And thermodynamic average gives you this simple formula. Now, this red line is what Nirmal got from experimental data by carefully subtracting this interpolation. In fact, what he did, it was a little bit more systematic, if not more accurate. He took this line and then took this line and then interpolated linearly between them. And then interpolated, and then applied the same procedure to this formula that I derived. And that's what he got. Fantastic agreement. Now he has, he can also extract this constant, which is the amplitude of this, not this constant, it's just the total amplitude of this whole of this effect as a function of temperature. And if you plot it, it's basically linear. So this dependence on magnetic field is reproduced through dependence of magnetic moment and H, and the dependence of temperature is also reproduced. So in summary, I'm closing to the end of my talk, but I have a few slides more. So this, we explained variety of observations, continuous variations in field parallel to C, different manifestation of this strong magnetic anisotropy. We explained three major magnetic phases, found total agreement with neutron scattering, including intensities, and we found a mechanism that explains topological Hall effect, which appears only through fluctuations, through selectively exciting of magnets propagating in particular directions, and that's quantitatively consistent with the experiment. There are some observations not explained, and that is nature of exchange coupling along C, why it is promoting spiral, and that's actually, you can speculate that it might be related to some sort of RQQY-like susceptibility feature. I didn't click. It's very hand waving. Also, it's also not very instructive to look at the Fermi sources because real part of stability is integral over all energy. But you can see that, for instance, there are pockets which are separated by roughly 0.25 ordering vector. Why do you have continuous variation of one of the magnetic ordering vectors? We don't know, but there is one speculation that fluctuations may actually be decreasing J3 over J1, and then you can move across this field, across this part of the parameter space like this. The splitting of these spirals in two, increasing with temperatures. I probably won't have time to go, and that's tangential to the topic of the talk. There are some speculations that how that can come from fluctuations of the vector directions in two different cases, in case of helical and cycloidal spiral. And there's competition of phase space, because for one of them there's more phase space, but the other type is favored by anisotropy. And this is nature of two phase regions near Tn, which we now know what the structure is, but don't have an explanation to that. But it's definitely clear that fluctuations play very important role, not only for generating this topological Hall effect, but also in making this phase diagram somewhat more complicated. Now, aftermath. When this paper was submitted, one of the referees were friendly, but one was the one saying, sort of like scratching their head, your mechanism is so simple, transparent, and it seems to be universal. Why has it not been absorbed before? Why only this compound? And our answer is like in this old joke: first, I've never borrowed your lawnmower owner. Second, it was already broken when I took it. First of all, it is not that universal. First of all, it needs to be a good metal. It has to have transverse conical spiral as a ground state in a relevant range of fields and temperatures. Otherwise, it does not work. And the spiral has to couple strongly with the conduction electron. You remember one of my first slides. It wants to be itinerant. So all sorts of complicated spirals with F electrons have to go out. And second, it actually has been absorbed. So this is one paper which was published before ours, and that paper has features unidentified antiferromagnetic phase here in some particular range of temperatures, and they also measure topological Hall effect, which they found by doing this not always accurate subtraction procedures. They found definitely some extra contribution in within this range, which was also strongly temperature dependent, was rising with temperature. They didn't know what how to explain that. Later, and they write, as I say, literally, we assert that there's likely a non-coplanar magnetic moment at low field. So that's sense topological contribution. Now later, very nice paper from Hui-Bukao group did full neutron scattering measurement on this material, and they found that there is no non-coplanar phase. In fact, when they found that two different magnetic structures produce equally good equally good fit to neutron scattering, but only those two. One was the amplitude wave like this, and the other was the helical spiral, just as we discussed in this manganese compound. Due to some circumstantial, probably incorrect reasons, they selected this one as more likely ground state. But from Newton point of view, both were very likely. We did calculations for the same material. We found the spiral with a wave vector very close to the experiment, and we mapped the all three-dimensional space for doing the spiral calculations, and this is a minimum. It's quite deep minimum, and it has a factor. Whatever agreement factor neutron is basically the same as for incommensurate spin density wave, amplitude density wave model that they used, and so this is this is experiment, this is our calculations. Yeah, and the amplitude wave has much higher energy, so was absolutely unstable. There's no question in my mind that this system does have helical spiral, which obviously flopped. They, for some reason, they did not draw this line, but it's very clear in their data that there is a spin flop transition at some small field, and that's exactly where they absorb the topological Hall effect. So their data are much noisier, and that's not their fault because the samples are not nearly as good formed as these manganese samples. But you can do the same procedure for couple of temperatures, and the agreement is not as fantastic as there, but it's pretty good agreement. And also you can see that the temperature dependence is roughly linear. Now, another paper was published essentially parallel to ours. That's another material. There they actually determined the magnetic structure in the finite field, and it's exactly transverse conical spiral as we wanted. And then they measured this topological Hall effect, again with this caveat it was extracted through this not well justified procedure, and they find exactly the same story. It's basically linear with temperature. And by the way, you can see that there is this little dash line here. That's another phase. That's another phase which is plays a role of our fan phase. So that's arrests the development of this topological Hall effect. So it develops only in transverse conical phase and also follows the same formula that we derived. So this is, yeah, that's what they're saying. They say present and tilted angles, meaning this transverse conical spiral, will mean that non-zero chiral spin configuration won't producing emergent magnetic field. Well, it will not. We know it's easy to show that one single transverse conical spiral does not produce it, but this fluctuation-driven sort of nematic effective field will. And then my finite example is actually a negative example. That's a paper from, again, from D2 group. They found that this is a helical structure here, and it's helical. And then with a higher magnetic field, it flows directly into fan phase. We are working hard trying to understand why does it happen, because magnetic anisotropy is actually not large there. It seems that coming from this particularly weird long-range interaction. But anyway, that's experimental fact. And when D2 John was giving this talk at George Mason University, I asked him if they looked for topological Hall effect, which is not discussed in the paper. And he told me that they did and didn't find any. So that's sort of negative confirmation of the same theory. This is one compound, very similar magnetically, but it just does not have this particular phase, has all other phases, and it does not have topological Hall effect. So basically, the answer to the question is where are these fluctuation, dynamic, nematic, whatever you call it, topological Hall and scalar chirality? They're actually hiding in plain sight. And don't laugh at this paper, because this article is actually published by Northrop Grumman, which is the biggest defense contractor of the United States, and then apparently believe in invisible aliens. But yeah, anyway, I'm finished there, and I'm open for questions.
Okay, thank you very much. Even hiding in plain sight. I don't know which the areas will be. Thank you so much. So we're open for questions. Please raise your hands, and then we'll start maybe with Igor Rosansky. So Igor, can you, I think, oh, did I not promote you? It's okay. Igor, can you go ahead and unmute yourself and ask the questions, please?
Okay, thank you. My question is, so if you are saying that there is a substantial contribution to topological Hall effects from the fluctuations, would you expect that in the vicinity of the phase transition between different phases, there would be an increase in the topological Hall effect, and whether there are any data supporting that?
Yes, I mean, this is, of course, it doesn't work exactly, but you can see, for instance, here, this is this phase transition, and the maximum is absorbed very close to there. You can look at this other material, which is, well, this is our material, and you can also see, hold on, let me flop it here. Where was it? Yeah, so it's, I don't know. No, I mean, it's a very simplistic theory, and it's not an, there's no abrupt change at this line, but it's quite obvious that as you try to approach this, as you go closer and closer, these fluctuations, it's just thermal excitement fluctuations. These are not fluctuations which are responsible, which are somehow related to the order parameter of the phase transition, just to make clear. So there's no direct contribution from there. But as you increase temperature and approach this phase transition, it is increasing, and then when you come very close, it stops. But these are just plain thermal fluctuations. These are not I don't know what would be the fluctuation responsible for this transition between transverse conical spiral and fan phase. But this is, and also the closer you are to saturation, the weaker this effect is, because basically the closer you are to actually saturated ferromagnet, the weaker is the amplitude of this possible of these spirals. So that's another thing. So it actually has to go to zero when you get into forced ferromagnetic regime. So I would say that qualitatively it's clear that it's fluctuations, but it's not directly related to the borderline.
Okay, thank you.
We cannot hear you, Jairo, now.
Igor, go ahead and ask your question. Sorry.
Great. Thanks, Igor, for your nice talk. I have two quick questions. One is to the Kagome ferromagnetic planes in the beginning of your talk when you were showing this interesting material. So why is it ferromagnetic, these planes? Did I understand it correctly? They are in plane, they are all ferromagnetic, yeah?
They're all ferromagnetic and quite strongly ferromagnetic that I have calculated coupling. There are also some spin wave measurements, and they all agree there's strong ferromagnetic coupling. I think it's just because it's a good metal in the plane. It's like metal iron.
Okay.
So, it's simple dynamic thing. This is electrons. If electrons are very mobile, they don't like to move on antiferromagnetic background. They like ferromagnetic background.
Okay, I see. So it's a good metal. Okay. Yeah. And the second thing, can you go to the crystal or to the spirals? Because I would like to understand when you said you apply the magnetic field along the C direction. And then how should I imagine the whole plane? So in which direction is happening the transport?
Well, I mean, it's a three-dimensional metal. Transport happens in all directions.
Yeah, so are you saying that, yeah, but in the experiment, I guess you have some orientation, yeah? So you have the magnetic field applied along the C axis, yeah, of the crystal.
You mean when they measure Hall effect?
Yeah.
Yeah,
when they measure Hall effect, I mean, there's interesting things happen when they apply magnetic field along X. So that basically creating this transverse conical spiral. So magnetic field is along X, and I believe, I think they measure conductivity along Y.
So the crystal this is a bulk crystal?
Yes.
This is bulk crystal. I apply field along X, you say, and measure along Y.
Yeah.
Okay, I have to think about it. But
I mean, to be honest, I don't exactly remember how they what the experimental said. The magnetic field is definitely along X, no, I think current is along Y. Yeah, but I mean, they measure all various directions, and this is there's one direction which they have, and the only thing I say is that we checked, and this direction is consistent with this idea of magnons propagating in the plane and perpendicular to the external field. So that actually generates the topological field of the right direction to explain their Hall effect.
Yeah, so these magnons are normal magnons. These are not some bizarre.
No, these are normal magnons. Yeah. But the point is that if these magnons propagate along Y, so in the plane perpendicular to magnetic field, then they can propagate along Y or along minus Y. And in external field, thermodynamically, one direction is more excited than the other.
Mm-hmm. Okay, thanks.
So let's go first with Kimelsky, and then we'll go with Jose. So Kimelsky, go ahead and ask your question.
Do you hear me?
Yeah,
okay.
I can. Привет.
Igor.
Hi.
Very nice talk, but I have some not question but comment. Do you try to propose to experimentalists? We both know this compound manganese gold 2, which if you dope it with chromium, you would have exactly plus plus minus minus cone.
Well, to be honest with you, that was on my shelf, and I was sort of make mental note to look into that more closely, but I haven't gotten to that so far. But
Yes,
you're right.
but,
I mean, this is potential candidate. I just need to look at that and analyze with this
no, but important that you dope it with chromium.
Right. I mean, we can talk about that separately. I know that it's that it might be a good candidate, but I haven't looked at that carefully yet.
Okay, thank you.
Okay, Jose?
Yeah, Igor, I had a question on your analogy to the nematicity in the 1 to 2s. So which was your point there? So are you expecting in the iron-based superconductors to maybe find this type of topological?
Oh, no. That was a very far-stretch analogy. It's essentially just another example of order from disorder. If you think about, you remember there's many famous works about nematic susceptibility, that basically you apply strain in the tetragonal phase, not in nematic phase. And you basically generate nematic crystal because there are always spin fluctuations with pi 0 and 0 pi, and they are equally populated without external strain, which plays the role of this external magnetic field. If you apply strain, that immediately, because they couple on Ginzburg-Landau level, that the fluctuations, let's say at pi 0, are excited more strongly than those at 0 pi, and that immediately creates a strong response to external magnetic field. So in this sense, it's analogous, but that's only in this sense. It's
but I have a question on, there is, as you know, there is one of these iron-based superconductors, the 1144s, that they have this vortex state. Of course, it's not conical. The question is, if you start manipulating disordered states with a magnetic field that you go into, let's say, a non-collinear out of plane type of order, could you then have a region maybe of finding this type of effect?
That's actually an interesting question. I would intuitively, I think probably not, but it actually is but you need to look at that more carefully. It's not that difficult because you have this vortex state, right? You know how it looks in plane.
Yes.
Now add and you can also describe that in continuous approximation as well, or you can do that. And then you apply magnetic field perpendicular to the plane, so they start cases. Then they become non-planar. Then the question is whether these conditions for scalar spin chirality will be satisfied or not. It's just to look at the structure. I think it probably will be still 0, but I wouldn't say for sure. So you remember where did I have it? Yeah, for instance, this.
Yeah, you need this to,
Right, yeah.
Okay.
I think maybe even some Raphael's paper, he actually wrote the continuous model explicitly. But then you need to add to this. So this now your M would be in AB plane, but non-collinear, and then you would need to add a component along Z to make it non-coplanar, and then calculate it. I doubt it will work, but you can check.
I can check. Thank you.
Awesome. So I have maybe a question, I have a curiosity. So in these systems, the disorder, say order from disorder, is the order now preventing you also from seeing possibility of some skyrmionic phases in the systems then?
Well, I mean, that's a matter of definition. There is no statically, there is no scalar chirality, so no skyrmion. But you can, if you want to visualize that, it would be like skyrmions appearing fluctuationally here and there, and then disappearing.
You have zeros, and then in that sense, have you looked in how strong would this be? Is
no, I did not look at anything quantitatively because I don't know any way how to calculate these coefficients. In particularly, most importantly, I don't know how to calculate the coupling. I mean, I don't know. Maybe other people how to calculate the coupling term between this topological field and external field. I need this term in Ginzburg-Landau expansion or in Hamiltonian to put into partition function, and I don't know how to do that. The only thing I can do is to just fit, say that there is overall scaling parameter which I can fit to the experiment. Maybe one can extract something from there, but I have no idea how does it how you can reformulate that in terms of Skyrmion amplitude. I don't know.
No, I was also thinking of in terms of moving and exciting some of the systems with currents, right? There you will fit to the experiment and get the ground state, and then from there look at the just essentially the possible spin generation, current spin generations that you can generate, and then couple it to spin transfer torque and spin orbit, not orbit in this case, but the topological one, to see if then you could excite some of the systems that way.
That may be. I didn't think about.
This linear responses, and so that you have already the ground state that you generate.
Right, yeah. Basically, you are saying that in this sort of quasi-nematic state, right? So this nematic state, how to probe this nematic state in a different way from topological.
You can generate a current, or actually like, the way around.
It might be possible. I don't know.
And then so cycle relations look at, say, if you inject a spin current, the spin pumping or something, which you excite them. So you can do, it's linear response after all. So you could possibly do that.
Yeah, I mean, it might be worth looking into that.
Yeah, because then it's the way to not just look at the phase diagram, but also to excite them. Okay. So I don't see any further questions. So all the 150 of you that showed up during this wonderful summer time that probably everybody's out and preparing for Eastern, we thank you. And thank Igor once again for a nice talk. And for the nice blossoms behind that, cherry blossoms that we have next week. And here we have them already, beginning to have it. And we continue next week again. I think I have to look up which is the next speaker next week. Sorry, I should know, but I don't, unfortunately. And I do wish you everybody a very healthy, and please stay safe. And I hope you get all vaccinated as soon as possible. Eastern with your family and friends, and I think Silvia Viola will be from MPI Erlangen will be giving a talk next week. And with that, we thank you all and see you in the other side. Thank you, guys. Thank you. Okay. Cheers. So Igor, I think everybody's listening maybe, but hang on, let me close here the streaming. And streaming.